Hey, good morning, afternoon, or evening, depending on when you're watching. Today is day 7, and we get into related rates with cones now. So, what changes from spheres, which we did last time, spheres only have volume equaling some related radius changing. Here with a cone, we have a radius and a height in there. So, there's two variables that can change when volume is changing. And so that means that we're going to have something added in here. We're going to have a unit conversion part where we have to write the whole equation in terms of one variable in order to do the derivative of it and differential parts. And we're going to do two different examples. We're going to do an example that relates a height versus volume question, and then we're going to do a radius versus volume question. So we're going to do two types, and then we'll do some practice with that as well. Okay. I think the practice will be tomorrow. As you can see, I got it there. Let me just pause here and check and see. I got to take a look at that practice, see how big it is. Okay, taking a look at it there, there's 6 of them there. So we'll probably do tomorrow will be for sure the way it'll work out. Because this will probably be in that 35-minute range or a little bit longer for cones. Even though there's only 2 examples, they take a little bit longer to do. Okay, so let's kind of get the formula out for what a cone volume is and kind of how the related rate changes with them. Okay, so let's start off by saying, first of all, here, go to marker here first, that for a cone, whoops, lost my. So for a cone, which is if we talking right cones, oh man, that's a bad one. Okay, we've got this radius in here, and we've got, that's perpendicular, that's the height. So the volume of a cone is equal to 1/3 pi r squared times the height. Okay, and that's our radius, our radius. That is our formula for volume. So you can see that there's 2 variables in there. It's not just r anymore. So now we have to relate, if we're going to do a differential and we got dr dt, then we have to relate everything into that variable of converting the h into an r. If we're going to relate everything and we got dh dt, we're going to have to convert the r squared into an h and so forth. And that's the extra step that's involved in here. Okay, so let me just bring up my little note here. Click that. Okay, so we're going to look at that basic example in our first examples here, using this and converting it over. And we'll do 2 different examples. So the first one we're going to do is we're going to do relating the height changing with the volume. So let me flip the page here. Okay, so it says volume and height. Okay, so a drinking glass is shaped like a cone and is being filled with the water at a rate of 15 cubic centimeters per second. The glass is 20 centimeters tall and has a radius of 4 centimeters. At what rate is the height of the glass rising in rising in the glass when the water is 9 centimeters from the bottom? So the first step that we're going to do is we're going to write down everything that we know first. So let's do this in green here. Green. Write the givens. Okay, so I like to draw a little diagram of my glass here. Okay. we know that the original size of the glass, which will give us the relationship between R and H, we know it says that the drinking glass is shaped like a cone, and the glass is 20 centimeters tall, which means the height is 20 centimeters. And the radius, it tells us, is 4 centimeters. Okay, and it says at what rate is the height of the glass changing? So we want dH dt. We don't know what that is. At h equal 9, because we're going to say the height is measured from the bottom up, right? That's what we'll say. Okay, because that's how it kind of fills up. And we know that the volume is going into there at a certain rate. dV dt is moving at a rate of 15 cubic centimeters every second. So that's what we've got to do first. We've kind of got all that, okay, all of the givens that we have. We want to find this. We know this. We have to now convert our volume equation into one expression. So in step 2, we're going to convert the volume formula, we'll say, for a cone into a one variable, either R or H. Okay, so we're going to do this using the relation of the glass 4 and 20. Okay, so we know that the volume of a cone is pi r squared h over 3, or 1/3 if you like, but I'm just going to put it over 3 like that. Okay, so we know that. And the ratio of r let's say of R to H in the glass. Okay, so we want to get the ratio of R to H in the glass. So that's fairly easy to do. Okay, there's our two measurements. So the ratio is of R to H is equal to 4 centimeters over 20 centimeters in the given glass. Okay, and now we're going to solve for a particular variable that we want to get rid of. So now we want dH dt. So we want to eliminate the R. So we're going to solve for R. Okay, so 20 R's. Okay, these cancel out the centimeters, right? 20 R's, got to be the same unit, obviously, equals 4 H's. Okay, so now I want to divide both sides by 20. So R equals 4H over 20. So R equals, if we reduce that, we can divide both by 4, H over 5 in the particular glass. Okay, now that can be plugged into the volume formula to get it in terms of H. So let's plug it in, do the ratio of the glass, and then plug into volume formula. Okay, so we're going to plug it into the volume formula now. Okay, so I'm going to plug it in where the r squared is. So let's move this down a little bit. So I got a little more space. Okay, so let's go ahead and do this. Okay, so we've got V equals pi times r, which is h over 5 squared times h divided by 3. Now we just got to do some algebra here. Okay, so pi h squared over 25. Okay, times pi times another h divided by 3. Okay, let's bring this over here to simplify. So we've got pi h cubed over 25 divided by 3. Pi h cubed all over 25, again divided by 3. So if we want to do that into 1, it's going to be divided by 3 is like multiplying by a third, so it's going to be pi h cubed over 75 for that particular glass. So there we have our equation for volume of that particular glass, not for any other glass but that one, because of the ratio of that glass, in terms of h only. So now we can use, in our final step, use the derivative. Okay, so step 3, use differentials or derivative to find dh dt. dh dt. Okay, so let's go ahead and do that here. Again, I'll make some more space. It's a longer question. Okay, so we're going to go with this formula right here. So we're going to take the derivative of volume with respect to time equals, this is a number, pi over 75. We'll write that out like this. And we'll treat this h cubed as h cubed, so that'd be times 3 h squared dh dt. Okay, there we got our derivative. We can do some simplifying with the 3 and the 75 for 25. So we've got pi over 25. Those will cancel out. Pi h squared over 25 times dh dt. And that's going to give us our dv dt. I'll put that in here. Okay, so now all we're going to do now is plug in our values now and calculate what dh dt is, because that's what we want to find. So let's go back up to the top here. I forgot what they were already. Okay, so we had 15 cubic centimeters a second at a height of 9. Okay, so let's plug it in. Okay, 15 centimeters cubed per second equals pi times 9 centimeters squared times dh dt, and this was over 25. Okay, so we have to reduce this number here so that we can divide it out on the other side. Okay, so let's take our calculators out. 81 pi divided by 25. Okay, you get 81 over 25 pi, which if we do that as a decimal number, okay, we're doing a little rounding here. It's 10.1 10.787, so we can say 10.18, okay? And that's centimeters, so this is 15 centimeters cubed per second equals 10.18 centimeters squared ddh dt. Okay, now we divide it out. Or if you wanted, you can keep the whole thing on your calculator and store it, and then divide out into 15. And I get 1.473. So we're going to get dH dt. We'll go to one decimal here. 1.5. And that centimeters squared cancels out a centimeter squared there. So you got centimeters per second. And that's the rate at which the filling of the glass is occurring. Okay. And that's our first example. That's using relating the dH dt1 to the dV dt1. We're going to do the opposite in our next example, okay? And then that'll be it for today, and then we'll go into doing some work with practice tomorrow. Okay, so today will just be the two examples of the two types of cone problems. That's the first one. Okay, so summarizing again, kind of what you go through is you should write down everything you know, get the size of the cup, and make a ratio of one of the variables to the other in the cone, the R to the H. Solve for the variable that you're trying to eliminate. Okay? Solve for the variable you're trying to eliminate. Plug it into the original volume equation to get the volume equation into one variable only. Derive that using differentials. Plug in your values for your differentials to calculate your result. Okay, that is what process for this is. Okay, one more question to go. We're going to do the opposite of what we did here, height versus volume. So we're going to do volume versus radius next. So let's flip the page here. Okay, radius versus volume. Okay, wheat is being piled so that the radius of the base is always 3 times the height of the cone. Okay, so they give you the ratio in this one. They're telling you what the ratio looks like. Okay, and then it says, what is the rate that is poured, the wheat? Let me fix that. What is the rate the wheat is poured on the pile if the radius of the base is growing at 0.80 meters per minute when the radius is 4 meters? Okay, so let's draw this one out, okay, and get our ratio and do all that kind of stuff. Okay, so this time we're going to be eliminating the H. Okay, so let me draw my wheat pile here. Okay, so I've got my radius on the bottom here. Let's make it bigger than that so we can see a little better. Okay, and then I've got my okay, now it says the wheat is being poured so that the radius is radius is of the base. Oh, I got too many is's in there. Man, my typing was bad there. Wheat is being poured, so radius of the base, not is always 3 times height. So that means the radius is always 3 times the height. So this would mean if this was 1, this would be 3. Okay, so that's basically what they're saying there. Okay, radius or the height would be 1/3 if you like, if you're going to go that way, right? Okay, so now let's go ahead and write in what else we know. It says, what is the rate the wheat is being poured on? So we want dV dt. We don't know what that is this time. Okay. If the base is growing, so the base dr dt is growing at 0.80 meters per minute. Okay. And we can say that we also know that that is occurring when r is at 4.0 meters. Okay, so that's what we know about this question. So now what we're going to do is we're going to kind of do our ratio next. So our ratio of r to h equals 3 to 1. Okay, so in this case, we want to eliminate the h, so we have to get what h is equal to. So we'll cross multiply 3h equals r. So h equals r over 3. Okay. In this case, that's what this here situation was. Okay, so now when we've got that, we're going to take the volume. After we've got the ratio, we're going to take the volume equation. The volume equation is pi r squared h over 3. And now we're going to plug in this value where h is. Don't forget the square there. Where h is to get our result of our volume for this particular question. So volume equals pi r squared, h is r over 3 divided by 3. So if we do that one, we got pi r cubed over 3 divided by 3. Okay, and that's going to equal, if we do the combining of those two together, finally we got volume equals pi r cubed over 9. Okay, and there's our volume equation that we're going to be using for this particular pile of wheat right there. So now we're going to take the derivative. Okay, so that we can plug in what dr dt is at a particular radius and figure out what dv dt is. Okay, so let's go ahead and do that. So here we go. dv dt is equal to, okay, so we're going to go pi over 9 is a number. Then we're going to take the derivative of r cubed. So that's 3r squared dr dt. Okay, now we're going to simplify this a little bit. dv dt. Okay, we can cancel 3 out of each of those. So this would be pi over 3r squared. So pi r squared over 3 times dr dt. Okay, now we know what dr dt is, so we can plug that into our equation. We know that the r is what the r is as well. We can plug that into our equation, and we can calculate dv dt. So subbing our numbers in next. Okay, so we're subbing in our values. So dv dt, okay, we don't know what that is. That's what we're trying to find. That's going to be equal to pi. R is 4.0 meters squared divided by 3 still times our dr dt, which was our rate for that. I forgot what that was. I'm going to look it up. 0.8, I think. 0.8 meters per minute. So we're going to get meters cubed per minute. Okay, so let's do our calculation here on our calculators. Okay, so 16 pi, 16 pi, that's 4 squared, which is 16 pi, divided by 3 times 0.8. Okay, and I get 64 over 15 pi, or if we want it in decimal form, we can say the dv dt equals 13.4, I'll go, meters cubed per minute. And that's the rate at which the wheat is piling on that. Okay, so there's our second example, and we're about 27 minutes in. So that's not bad, actually. Second example. So those are the two type of cone problems. So I'm going to leave that cone work tomorrow because they take a little longer, I think, than the Saphir problems. And I've got 6 of them in practice. And the next day, let's go and take a look at those. So today, you can get started on them if you want, if you got extra time or whatever. But I'm going to leave a work period tomorrow for day number, day number 7 that we did this one here? Let's see. Okay, so day number 8 is going to be a work period for cones. Okay, and when you get into day number 8, there are 6 problems here, and I'll put the answers up for them as well. Okay, here we have some cone problems here. Do you have to do all 6? Well, no, probably not, but I'm giving you a work period. It is important to get the related rate stuff. So that'll be tomorrow. So tomorrow will be a work period on related rates, and today was our video. So we'll stop the video at this point. Again, if you ever have any questions, feel free to ask or get a hold of me if you have some questions that you need answering and things like that. Okay, so we'll work period tomorrow. So make sure that you guys are at least trying a couple of those, okay?